So welcome back to day 5 of Calculus 1. And we have the topic of the day, more fun with limits. We'll look at some very interesting ones today. And I just want to remind you, most of the stuff we're doing right now is in the category of an intuitive type limits, where we have some graphical idea of what the limit should be, or we have a numerical idea of what the limit should be. And once in a while, we have an algebraic idea of what the limit will be. And on Thursday, we'll look at a more formal definition, which really nails down what a limit is, but it's pretty tough to work with. So what we're going to do is just accumulate a set of rules to work with. And so I'm just going to go over some of those rules that we need to know. So if I take the limit, let's say as x goes to 5 of the function y equals 7, right? So think about that, y equals 7, it's just this horizontal line. It doesn't matter what x is, y is always 7, right? So the moral here is that anytime we take a limit, doesn't matter what x is doing, so x could be going anywhere, and we have some constant, just a constant, then we just have a constant. Okay, that just hangs out. Another powerful one that's kind of basic, so these are the basics here. If we take the limit as x goes to, let's use 5 again, of the function just y equals x, well, y and x are always the same thing, and so as x goes to 5, x goes to 5, so the answer is just 5. And so the general form there, limit as x goes to any number of x is that number. Some other things that popped up when we were playing around were limits related to infinity and 0. And so if we take, for example, the limit as x goes to 0 on the right side, so remember we have one-sided and two-sided limits of, say, 1 over x, when we flip a very small number, it becomes a very big number. Like if x was 1/1,000,000th and we take the reciprocal here, we get 1,000,000. And so this thing goes to infinity, which is a special way of saying the limit does not exist. But we can say more than it just doesn't exist. We can say, hey, it actually increases forever, right? Which is important information. So it doesn't exist in a special way. And so that is an important one to know. A couple related to that is if we take the limit as x goes to 0, but on the left side of 1 over x, then we get what we call negative infinity, which also does not exist, but the moral there is that it decreases forever, is what that really means. We're dropping the y value. And then the reverse of those two would be, say, the limit as x goes to infinity of 1 over x. If we take 1 over a really big number, we get a really small number, and the smallest number you can get is 0. So here I have an infinite limit, but I have an existing value. Do we ever get to 0? No, just like we never get to infinity, but that is the limit. We can't go past it, but we can get as close as you want forever. Okay. So just a note here, we don't actually get to 0. But we can get as close as you ever want. And that's kind of the essence of a limit there. We can get as close as we ever want to whatever the limit value is. Sometimes that's numerically, but sometimes it's algebraically too. Now, oops, wrong button. I keep referencing y values because this is a study of limits of functions. So we're working with functions here. And so let's suppose we have a couple of functions. We have one function, y equals f of x, right? And we have another function, y equals g of x. And let's say both of these exist near, the y values exist near x equals a. And even more than that, if I take the limit as x goes to a of f of x, it exists, and so I get a particular number we're going to call L, and then we're going to do something similar as x goes to a, g of x is going to resolve to, let's say, this number m. So L and m are real numbers. Right, the limits exist. Okay, so there's no infinity going on here. We have actual numbers. A is a number, m is a number. So as long as these conditions up here are true, then we get a bunch of special properties for limits. Sometimes they're called laws or rules. I'm going to call them properties today. If I take the limit as x goes to a of f of x plus g of x, assuming the limits exist, that's the same thing as splitting up the limit over the sum. You could say the limit distributes of f of x plus the limit of g of x, both as x is approaching a. And again, each of those has values, so we can say the answer has to be L plus M. Again, the limits have to exist. They are L and M, whatever those two numbers happen to be. Now, there's nothing that special about addition compared to subtraction, so this is true for plus or minus. And so we can turn this into two rules into one. It doesn't matter whether we're adding or subtracting the limit of the sum of two functions or the difference of two functions. It's the limit of the sum, the sum of the limits or the difference of the limits, which resolves that way. And we'll look at a bunch of examples of this in a minute. Another powerful one is the limit as x approaches a. If I take any multiple of a function, like some constant times f of x, then that constant really doesn't affect what's going on. It's just a scaling factor, so that's the same thing as the constant times the limit. Which is just going to be c times L in this case, because f of x is going to L as x goes to a. Just like addition is nice, repeated addition is multiplication. Multiplication turns out to be nice. So the limit as x goes to a of f of x times g of x is just going to be the product of the limits. Which is just L times M. Division works nice too. So the limit as x goes to a of f of x divided by g of x is going to be the quotient of the limits. So limit x goes to a of f of x over the limit as x goes to a of g of x, which should just be L divided by M, as long as M is not 0. Another catch is if M was 0, L couldn't be 0 at the same time. So it's sufficient, and we've talked about 0 over 0 versus a number over 0. We'll look at that again today, the difference between them. But the main thing here is we don't want the denominator to be 0, because then weird stuff happens, depending on what the numerator is. Either infinity is involved or some other indeterminate thing we have to resolve. So these are the main ones right here. We have those other two basic cases on the previous page, and then a couple of other interesting ones related to this are when we work with powers and roots. And remember, powers and roots are really the same thing because a root is just a fractional exponent. So if we take the limit as x approaches some number of f of x, the function, raised to any power n, that's just going to be the limit f of x to the power, which is just L to the power n, because f of x is going to L as x goes to a there. So the limit can kind of slide into the power, even if it's outside, which is kind of nice. And really, since a power is a root, the root rule is a consequence of this, which need not be stated, but let's say n is a whole number there, then we do need another rule, and that would be the limit as x goes to a of the nth root of f of x is going to be the nth root of the limit as x goes to a f of x, which should just be the nth root of L. Now, one thing to consider here, though, is even roots and negative numbers are kind of a pain, because then we have imaginary numbers, but it turns out imaginary numbers are fine too, although in this class we're mainly just focusing on real numbers. So I'm not going to worry about that side case there. So those are all of the limit properties, and so we're just going to play around and use them in a few different contexts. And the one that's kind of nice to apply it to is this makes working with polynomials and rational functions relatively easy, as long as 0 isn't involved for rational functions, and we'll look at more cases of that in a moment. So polynomials are nice. When working with limits, and hopefully you remember back from your college algebra days that polynomials have a domain of all real numbers, and partially because of that, the limits work out well. So if we had something like the limit as x is approaching -2 of x squared plus 3x plus 4, and technically we should put that in parentheses there, then we can break it up to the limit of each part. So this is the limit as x approaches -2 of x squared plus the limit as x approaches -2 of 3x plus the limit as x approaches -2 of 4. And then each of these I can apply another rule to. Like here I have the limit of something to a power, and so I can pull that power out. So I could rewrite that as the square of the limit as x approaches -2 of x. This one right here, the multiple of a 3 can pop out. So that could be 3 times the limit as x approaches -2 of x. And here, well, it's always 4. It doesn't matter what x is. I'm just going to jump and say, hey, that's just 4. Here, x is approaching -2, so x is -2. So I would have -2 squared. Here, the 3 is just chilling, waiting for the limit to resolve, which resolves to -2, and then plus 4. And so -2 squared is 4, plus we have, what, a -6 there, plus a 4. So on a good day, that should come out to 2. Yep. And so I mentioned the other day, a lot of times with limits, we cheat by plugging in the number. And it turns out these limit laws give us tools to cheat, essentially. So oftentimes, I'm not going to write all of these steps down. I'm just going to try to evaluate at the given number and see if it exists. And yeah, 2 definitely exists. It's a number. Rational functions. Oops. As long as a limit of 0 isn't involved, rational functions are pretty straightforward, kind of like polynomials. So if I have the limit of x as x goes to 3 of, let's try 2x minus 1 over x squared plus x, the rule says as long as the numerator's limit exists and the denominator's limit exists, then this should resolve. And the only way to know if they exist is to check. So we just have to check, either do or think. Take the limit of the top as x goes to 3. Take the limit of the bottom as x goes to 3. And again, the limit sneaks into the sum, the limit sneaks into the difference, the constant pops out. So it's basically just arithmetic at this point. So I'm going to skip a few steps and just say, hey, if I plug in 3, I'm going to get 6 minus 1 or 5. If I plug in 3, I'm going to get 9 plus 3 or 12. So this limit, since the numerator exists and the denominator exists, must resolve to 5/12. And when we're unsure of something like this, we don't trust our arithmetic and our algebra here, can always graph it and plot some values to check. So let's just, for fun, double check that that's the case. And I'm going to use GeoGebra, Desmos today. I did remember how to scale the axes independently in GeoGebra, which is a feature I like that Desmos doesn't have easily. They just move the button on me. So I have this function f of x, which is a fraction. And what do I have? 2x minus 1 in the numerator, and I think it was x squared plus x in the denominator. Oops. Squared plus x in the denominator. So this is a cute function. It's got this nice vertical asymptote here, and it's got a horizontal asymptote, which is a whole other area of study we talked a little about last class. And what I was just wondering is, hey, does this function actually exist? 3. And the calculator says, yeah, 5/12. Cool. No problem. Problems we would have are any number where the denominator is 0. And that's another issue we'll get to in a moment.